All right. Oh, wait. Get your lights. All right, questions, because we're in a chapter, into 5, beginning of 6. They overlap. I'm going to go through some stuff. I know somebody asked me about the solutions. It was Mason. And I put them up for chapter 6, so everything's up there for you to do. I know we have a break coming up. Somebody sent me an email, I think it was you, Jeremiah, that wants the quiz moved to Monday. Well, it won't be next Monday. It would be the Monday of the last week. Isn't that the last week of class? What I'd prefer is have it on Friday, and then the last week of class, get the makeup final in for everybody, and we'll replace the lowest grade if you have taken all the quiz. If not, it'll make up the quiz you missed. Y'all with me, class? I prefer to do it that way, so you get a quiz Friday, then that quiz, makeup quiz. The quiz Friday is going to be on the material we're covering right now with propagating waves. And if you keep up with it, it shouldn't be too bad. It's straightforward. You asked me about curl equations. I will put them, but you probably will not need it. Go ahead.
How's the makeup work? It's just like a random quiz.
It's a quiz on the most recent material that we covered.
Oh.
I try to do, I've done things in the past. All right, the quiz, the makeup would be all-inclusive. That's a disaster. The final is all-inclusive. We have a lot more time to study. All right. So, first questions before I get going. I gave you some problems. One in chapter 6. Did you have a question? Anybody back there? I'm just curious how many tried them? A lot of what? Curl kind of crap, right? In chapter 5, but chapter 6, it isn't. What I'd like to do is go through some of the derivation stuff, and then I'd like to do some problems if you don't mind. If you have questions, I'd like to, please ask. Don't wonder, ask. If you have it, chances are a lot of people have it. All right, so we started out, and you don't need to write this part. This is just to bring everybody on the same page with what we're doing. We start with the two Maxwell's equations. Curl of H is equal to J plus the partial D with respect to T. These are vector equations. Curl of E is equal to minus dB dt. And this is, again, just, you don't need to write them down. These are two equations. Briefly, what do we call this guy right here? We reference it with a name of a man. Ampere, right? Ampere circular law. What do we call this one? Faraday's law of induction, all right? Just try to reinforce this. Then we use the coupling equations. We say J is equal to sigma E. Really, D is equal to epsilon E. We do B is equal to mu H. These are coupling equations. These are all vectors here. The epsilon, sigma, and mu are just scalar parameters that are dictated by the media it's in. Sigma of free space is always 0 in a vacuum. There's nothing, no charge that can conduct current. After that, I do one other thing. I go to the phasor domain. So anytime you have a d dt, it becomes just j omega. And I went through that last time in detail. Y'all with me, class? Bringing everybody up to speed. So the next step here, when we take these things and we get one equation, I'll take this equation first, and I get curl of E is equal to, and this becomes minus j omega mu times curl of H, and here I replace the time derivative with j omega. I replace B with mu epsilon. Y'all follow me? And I take another curl. This is exactly what we did last time. We go ahead and we say if this equation right here will become curl of H is equal to sigma plus j omega epsilon times E. This is going to the phasor domain and replacing D with epsilon E and the time derivative with j omega and replacing J with sigma E and then factoring out the E. Does everybody remember this? If you didn't go through it, just try to make a mental note. This is what we do to get where we want. From this equation here, I replace the curl of H with that, and then I get curl of E is equal to minus j omega mu. Curl of h is there, is sigma plus j omega epsilon e. Now we have one equation, one unknown. Now the next step is to simply simplify things, breaking this curl up into the gradient of the divergence of E minus del squared of E. You don't need to write this down. This is in the last lecture entirely. I'm just replicating. You all with me? That's equal to minus j omega mu times sigma plus j omega epsilon times E. And at this point, I'm going to stop and say, when I get to this point, to continue further in a meaningful way, I have to make some assumptions. Y'all with me? So, you remember the divergence of D was the charge density, right? If you replace D with epsilon E and assume epsilon does not vary spatially, you get div of E is equal to rho V over epsilon. Does everybody remember me doing this? What do we call this law here, by the way? Anyone? Begins with a G. Gauss. Gauss's law. All right, so that's the relationship. Then, at this point, we say that rho V is going to be assumed 0. Y'all remember that? It's charge neutral region. You can have positive and negative ions that can convey charge, but the net, if you took any volume of space, the net amount of positive and negative charge would be 0. They would add to 0. Y'all follow me? Nullify each other. That's important. So we assume this, and that means it gets rid of this thing, right? Remember that? If that's assumed 0, that's gone. Div of E is 0. The gradient of 0 is 0. Then we come here and we start modifying things. We create a new constant. This is called gamma, and it is the propagation constant. And it is equal to alpha plus j beta, and it's equal to the square root of j omega mu times sigma plus j omega epsilon. Everybody follow me on this? Now, that propagation constant is the same symbol in a very similar formulation as it was back in the day when we did transmission line propagation. Alpha is the attenuation constant. Beta is the wave number, radians per meter. Do y'all follow me on this class? You remember this? How many of you actually remember, at least have an idea where I'm going? All right. Now, at this point, come up here, take this equation, we do one other thing. We assume plane wave propagation. All right, now, did anybody read through the book in the last part of 5, first part of 6 on plane wave propagation? Anybody? Anybody look at that? You'll notice he doesn't go into a great detail, but he just says, this is what we're going to say. The E field is only oriented in one direction, and that's the X direction. That's the polarity, but it's moving in the Z. We're making this assumption. Now it could be plus or minus Z. So we have plane wave propagation, and from that, we take this equation and we rearrange it, take the del squared on this side, and you end up with this, del squared of E minus gamma squared of E equals 0. That's called the Helmholtz equation. It's a wave equation. This is in the book, by the way. And I think I put all this up there last time. I'm just reminding everybody. At that point, then we take this, and based on the assumption that we have plane wave propagation, it's propagating in the plus Z direction or minus Z, plus or minus Z, and the E field itself only has an AX component. It's vertically polarized, but propagating in either the plus or minus Z direction. I'm going to stay fixed on the plus because it'll be easier to see the relationships. Y'all with me? Okay, now this becomes the second derivative of EX with respect to Z squared minus gamma squared EX equals 0. That's the differential equation I talked about a little. That is a homogeneous differential equation. Can anybody tell me what homogeneous means when we're talking with respect to differential equations? Anybody? It's equal to 0, right? All this, the variable differentials and the actual function is 0. Now, if I made this non-zero, it's inhomogeneous. Or it's, sorry. Here we go. It's a homogeneous differential equation. And it is, I forgot to state on this, but this is fundamentally something where it's a linear electric field. It's a homogeneous differential equation. It's equal to 0. The solution can be found by assuming e to the lambda z. Do you remember me doing this stuff? And then you finally, without going through it all, you're going to get solutions of the form e itself will be some ex0 positive e to the minus gamma z plus some ex0 minus e to the plus gamma z. And you get that. I think the word homogeneous, when they talk about differential equations, there's another term I'm looking for and I can't think of how to. It's equal to 0. That's the standard one you solve. Then you find the particular solution if you have an actual constant that's equal to or some function. Do y'all remember that? You have to get the 0 solution plus the other one. Add them together and then solve for the constants. So this is the E field that's in the AX direction. That's the E field, and that's where we were. And then I went to the time domain. Do y'all remember when I did that? And I talked about just propagation and the, well, actually I showed both parts of propagation. If you had positive and negative propagation, I'm just going to write it down one time here, and I'll take it from here and get to the point. Now, I don't know how much you had in physics about this, but physicists usually do something where they're going to solve a second order differential equation in both second order space, second order time, and they get a solution that's called the wave equation. How many remember that in physics? Didn't you have this or not? I don't know what they teach, like with the rope moving, the propagation on a rope, it's a second order differential equation.
Oh, they didn't break it into differential equations.
They did?
Because by then we were only taking Cal 1.
All right, well, I'm not a person to say much about that because when I did this stuff, physics was sort of, it was the key course that you took, and you took, I think, these are quarter systems, so you took 4 quarters, a year and a quarter of physics, and you had to have fairly good grades to be accepted in the engineering, because if you're not good at physics, you're going to be horrible at engineering. That's the idea, and it is generally true. All right, so back to this thing. Now you've got that equation, and I'm going to say that's you have that in as a function. It's in the frequency domain. It's a phasor domain equation over there. You all with me? In the time domain, it'll look like this. You'll have E of zt equal to some E x0 positive, and then it will be e to the minus alpha z cosine of omega t minus beta z plus ex0 minus times e to the plus gamma z cosine of omega t plus beta z, and it's in the ax direction, the orientation. How many remember that? How did I actually get from that step to this step? There's one key part. Do you remember? What domain is this in? Phasor frequency. Right? What do we do to get the time domain form? E of zt was equal to the real part of e to the j omega t times the phasor domain part. And I'll even put a tilde over here. Times e vector phase. How many remember that? Right? Then you use Euler's identity from that point to get the 2 cosines. Do y'all remember that class? I'm just trying to bring you up to speed. You're going to have to know this stuff, and you'll see it over and over again. Depending on the route you take, I suppose if you're strictly a digital engineer, you won't, but in most cases, all this stuff overlaps. You don't have just somebody that does I don't know, circuit layouts or something. Okay, back to this thing. Now we have this. Which way is this one propagating in y? The first term. Anyone? Positive z, right? So it's plus z. And this one, minus z. Now, this, by the way, it's a general form of the equation. If nothing's propagating in the negative direction, then Ex 0 minus is 0. The whole thing goes away. We're going to start there, and we're going to say, all right, now we're going to take a look at the relationship between E and H for a propagating plane wave. Remember, with a propagating wave, the E field itself, or I should say the propagation is in one direction, and it looks, if it's propagating that way, if you took a plane perpendicular to that direction, the E field itself would have the same magnitude, phase in it, as it does at any one point on that constant Z surface. This is real important. Y'all with me? So it's plane wave propagation. There is no curvature to the actual plane of propagation. So now if we only look at plus Z propagation. Write this down. I'm doing this to simplify some of the stuff. Otherwise, it gets a little confusing. So therefore, in the phasor domain, you have an E field itself. If it's plane wave propagation, some E naught x plus, or just E naught plus is good enough because it's going, we only have one component. E to the minus gamma z ax. Remember, gamma is alpha plus j beta. They're interchangeable. I'm leaving it as gamma for this one, all right? Y'all with me, class?
I had a question about the E of CT. So with the part moving positive and the part moving negative, is that measured at the same point, or is that leading?
Doesn't matter. I mean, well, for this, z is z, all right? So whatever z is there, that's z, that's z.
Yeah.
Whatever t is, that's the t, that t. It is at a point in space-time.
Okay, are we measuring its propagation away from an origin point, or?
No, we're measuring the value of EZT at a point in space-time. You don't know which way it's propagating unless you talk about the specific terms. That's only at space-time. And if you literally did something, made a movie of this, where you graphed magnitude of, say, the EZ of t for t equals 0, you're going to get something. Then let t, say, progress so that omega t will be like 30 degrees. You'll see the peaks moving in opposite directions, I promise you, if you do this. It's a good thing to do just to prove it to yourself. So if this is the E field, right? The H field itself can be found. And we're assuming only positive direction. You can take the curl of E, and remember, curl of E is minus j omega, right? And then it's going to be times mu times h. Do y'all remember that? Right? When you do the curl of E for this, we could put it up here. You're going to have ax, ay, az, ddx, ddy, ddz, then ex and 0, 0, because it only has an x component. You go ahead and do the curl. You get this term. You get minus gamma times ex0 e to the minus gamma z. Now that was in the x direction. Y'all follow me? But the curl of this will be in the y direction. All right, I'm going to put it down. A, y, and that's equal to minus j omega mu times h. Now, if you look at that for a second, you'll notice the polarity. I mean, we could do the curl, maybe I should, but I think it's unnecessary. You can do it yourself. It'll become, you know, when you take a curl of any vector, it's perpendicular to the vector you took the curl of. The curl of the vector is perpendicular. And this H field has to be perpendicular to the direction of propagation, which it is. Now, if you look at this right here, that H field can be gotten by dividing that by minus j omega mu. Y'all see that? I'm going to do it right here. I'll give you a second. I'm just trying to make a point here. Y'all see this, class? Now, you can see that the H field will have it will vary as e to the minus gamma z, right? Let me take a look, right? Did you have a question? Just ask me.
I was just trying to see what was that after the E.
Wait, you're asking for this